Good morning everyone. This is Dr. S. Sonia, Assistant Professor of Physics, Holy Cross College, Nagarkoil. Dear students, today I am going to teach you about atomic force microscope. So all of us are familiar about light microscopes and electron microscopes like scanning electron microscopes and transmission electron microscope. Also, we all know that the electron microscopes can only for conducting samples. For insulators, we can't use these electron microscopes. Similarly, those electron microscopes can produce us 2D images only. So, in order to analyze non-conducting samples, we should go for atomic force microscopes. So, outline of the presentation is history and development of atomic force microscope, and we are going to discuss about the different modes of atomic force microscopes and how the tip sample interaction will be takes place. First, let us see history and development. So, in order to analyze the non-conducting samples and get the accurate information of 3D images, the new technique was take birth in 1981 by G. Binning and H. Rohrer, that is STM, scanning tunneling microscope. So, for this new and innovative invention, they received the Nobel Prize in the year of 1986. So, as you can see in this picture, STM, there is no need of lenses, light or electron sources like scanning electron microscope, that is SEM, and transmission electron microscope TEM. Here we had a tip, surface and surface atoms and tip atoms. So, the principle used in STM is tunneling effect. So, we know that tunneling effect means crossing the barrier. So, here what is barrier? So, the distance between the tip atoms and surface atoms is called as barrier, that is mentioned in the energy diagram. So, here this is called as barrier. So, the barrier distance is taken as Z. Here the tunneling effect can be produced by simply applying the voltage between a sharp metallic tip and the surface of the sample. So, if this barrier is approximately a few atomic diameters thick, electrons are able to tunnel through it. So, therefore, there will be a current flow. If V of t is small compared to a work function pi, then the tunneling current IT of Z is equal to I0 into e power minus 2 kT Z. So, what is meant by work function? So, work function is an energy needed to remove an electron from a solid to a point in the presence of electric potential. So, here Z is the gap, and this tunneling current depends exponentially on the barrier distance or height. So, I0 is the function of the applied voltage and the density of states in the tip and the sample, that is taken as kT, which is equal to root of 2m pi divided by h cross. So, mostly for metals, pi will be 4 electron volt, and the most impressive feature of this new type of microscope is the extremely high spatial resolution, that is 0.01 nanometer can be achieved. So, also one can image even to manipulate individual atoms or molecules of the materials. So, scanning tunneling microscope is only for conducting samples, so therefore it is restricting its principal use to metals and semiconductors. So, now why we want to go for scanning tunneling microscope to atomic force microscope? So, already I told STM, which will measures only for measures the conducting surfaces, that means tunneling current, and where the piezoelectric transducers are used for scanning, and that will produce dramatic images of atomic lattices. But the AFM physically conduct the specimen, but STM do not. So, the success of STM gave birth to a large family of instruments. They generally referred as SPM, that is scanning probe microscope. So, here AFM is also one type of SPM. So, where the AFM works on a principle similar to a record player, and the tip is made by silicon and silicon nitride, whereas diamond is used in the record player. But atomic force microscope is a new and relatively cheap method of imaging objects from nano to micron scale. So it's a atomic force microscope is a broaden the technology to non-conductive surfaces, and the atomic force microscope is a synthesis of the mechanical profilometer using mechanical springs to sense forces, and it will measure the forces acting between a fine tip and a sample. So the tip is attached to a free end of the cantilever and is brought very close to a surface. So therefore there will be attractive or repulsive forces formed and from the interactions between the tip and the surface, and that will cause a positive and negative bending of the cantilever. So atomic force microscope, as I already told, that it is invented by Binning in the year of 1986, and it is the first working prototype in 1986. So the atomic microscope consists of a sharp tip at the end of a flexible cantilever that produces from a holder. So the tip is typically pyramidal or conical in shape with 10 to 20 nanometer size was located at the end of the cantilever. Probe is mounted on a piezoelectric scanner which can move in the X, Y and Z directions, which is used to scan the probe across the sample surface and produce image in 3 dimensions. So here the piezoelectric scanner is used to convert electric potential into mechanical motion. So what is meant by piezoelectric effect? Piezoelectric effect is the ability of certain materials to generate an electric charge in response to applied mechanical stress. Here, the interaction between the tip and surface is measured and converted into an electrical signal. We will get 3D image of sample topography. Here, the interactions will produce electrostatic, magnetic and chemical forces. For magnetic force imaging, that is MFM, the tip may be coated with iron or nickel. So, light from a laser is bounced off from the cantilever and photodetector. So from this signal we can measure the deflection of the cantilever. So how does the AFM operate? As we seen in the previous slide, atomic force microscope consists of tip, cantilever, piezoelectric scanner, detector, etc. So here as the tip is repelled or attracted to the surface by intermolecular interactions, that is forces, between the atoms of the tip and the surface, the cantilever will be deflected. The magnitude of deflection is monitored by a detection system. A feedback mechanism from a detector system will adjust the piezoelectric scanner and maintain either a constant force or constant deflection mode between the tip and the sample surface. It is depending on the AFM setup. So during the interaction between the probe and the sample, if the distance between the tip and the sample is very small, that is few angstroms, a strong repulsive force appears between the tip and the sample surface due to the overlap of atomic orbitals. Thus the repulsive force increases as the distance between the tip and sample surface decreases. So for example, imagine a pond where water is coming from the river as well as the tank at the same time and the same place, then what happens? Water will repulse from that place, isn't it? So same thing is happening here also. So when the tip scan the surface at this close distance, a piezoelectric scanner rises and lowers the tip to keep constant repulsive force between the tip and the sample surface, so that we can get high resolution image of the surface topography. There are different modes of AFM are used to acquire images. So according to how the AFM probe moves. So they are first one is contact mode, non-contact mode and tapping mode. So contact mode. It is also called as static mode and it will give high resolution images. So in the contact mode there will be a possibility of damage of the tip and sample. So it can measure frictional forces and it's always in very close contact with the sample surface. And then the next one is non-contact mode. It is also a dynamic mode, but the probe oscillates above the sample without the tip coming into very close contact with the surface. And in the case of tapping mode, it will give the better solution, and it is also called as dynamic mode or inter-emittent contact mode. Here the probe oscillates, only comes into very close contact with the sample. So contact mode is also called as attractive or repulsive mode, and there will be short range interactions will take place, and balance between the atomic and elastic forces and feedback regulation keeps cantilever deflection constant, and there will be a possibility of tip breakage or surface damages, and voltage record indicates height of the sample and not suitable for soft samples. So there in contact mode also there is the two different modes, that they are constant height mode and constant force mode. In the case of constant height mode, no feedback system will be used and height of the tip is fixed. And in the case of constant force mode, deflection of the cantilever is fixed and the motion of the scanner in Z direction is due to the feedback system. So advantages and disadvantages of the different modes of atomic force microscope. In the case of contact mode, we can obtain high resolution images since the distance between the tip and sample is very low. But when we are using the biological samples, we cannot use this contact mode, because when the tip is contacted with the surface, there is a possibility of tip damage. Since the cost of one tip is 3000 rupees, we should careful about it. So this problem can be overcome by tapping mode, and where the tip vibrates rapidly up and down according to the position of the atom. So but we cannot get that much of high resolution as getting from the contact mode, but we can reduce the tip damage. But in the case of non-conducting mode, uses long range of forces which are attractive, and these attractive forces occur tip and sample surfaces distances that is less than 10 nanometer. What we can learn from the atomic force microscope. So we can able to get the topography and mechanical properties, and also we will get the particle size distribution and 2D and 3-dimensional images, and we can able to get the substrate roughness, and the layer by layer coating can be analyzed, and pinhole formation or other defects in the oxides growth, and we can able to find out the grain size and stiffness, elasticity and adhesion via phase mode, and we can able to find out the Young's modulus of the sample, and we can able to study the changes in the structure by insight to atomic force microscopic analysis with the changes in temperature. So there are number of applications for AFM, so that they are beam deflection detection, force spectroscopy and nanolithography. So advantages and disadvantages of atomic force microscope. So we can take images in all the environments, air, liquid and vacuum, and interaction with the surface allows for measurements of physical properties of the surface, and the sample need not to be conductive, and atomic force microscope can deliver 3-dimensional topographical information from the angstrom level to the micron scale, and very high vertical resolution, and we can manipulate, and easy sample preparation, accurate height information can be obtained. And what are the disadvantages? It will be limited vertical range and limited magnification range, data not independent of the tip, and tip or sample can be damaged. Thank you.